Hello and welcome to my new video. This time again about fractals. Fractals are formed by repetitions of certain structural motifs on various spatial levels. They can be modeled by nested loops, with the inner loop defining these motifs on one level and the outer loop running through the various levels. As a first example, let's revisit our branched fractal structure from 2 videos ago. In this image, I have marked different levels with different colors. The structural motif in this case is a divergent set of two cylinders with one starting point and two endpoints. Here it is given for level 1. Each level contains the double amount of elements compared to the level before. With the nested loop approach, the inner loop is defining all endpoints for a given layer, in this case 2 endpoints, while the outer loop is running over all levels. In each outer loop, the endpoints of the previous level are becoming the starting points of the current level and the new endpoints are calculated. So, for example, we have 2 endpoints on this first level. When going to the next level, they become our new starting points and we have to calculate 4 new endpoints. In a similar way, we have to calculate 8 new endpoints for the following level and so on. I have detailed modeling these structures already 2 videos ago. In this video, I want to give you some further examples, which are all using this approach of nested loops. Let's start with this structure here. The basic motif is a sphere surrounded by 8 smaller spheres, all fitting into the enclosing box of the larger sphere. These spheres are then in turn also surrounded by 8 spheres, and so on. When trying to model this by a nested loop approach, we have to use the inner loop for modeling the basic motif and the outer loop for proceeding from level to level. Proceeding from level to level means that the novel small spheres become the new starting spheres and the number of elements to be calculated is multiplied by 8. This is not very complicated. You can look it up in the script on my GitHub account. The inner loop, however, where we have to calculate the geometry of our motif, is somewhat more complicated, and I will lay it out a bit more in detail now. Let's start with a simple cube of edge length A. First, let's talk about the face diagonal df. Its length can be easily calculated by using a rectangular triangle defined by 2 edges of the cube and the face diagonal. According to the theorem of Pythagoras, the square of the face diagonal equals the sum of squares of the edge length. Solving this equation for the f results in a length of a multiplied by the square root of 2. The space diagonal can be calculated in a very similar way, using a rectangular triangle from within the cube defined by one edge of the cube, one face diagonal, and the space diagonal. Again, we can use the theorem of Pythagoras for calculating the length of the space diagonal. Solving this equation for the s results in a value of the edge length a multiplied by the square root of 3. We keep these 2 equations in memory for later. The best approach for our geometric problem is focusing on the rectangular triangle we just used for calculating the space diagonal. Here I'm including the central sphere in this triangle. It is touching the upper and lower face, but not the cube's edges. The surrounding spheres will also be located on the face diagonal, again touching the cube's top or bottom, but not its edge. For building up our structure, we need to calculate the angle alpha for rotating the smaller spheres from an equatorial position into their correct position. In case you think this angle should be 45 degrees, you are in good company. I thought this first too. It is smaller than 45 degrees, however, and can be calculated by using the rectangular triangle indicated. Within this triangle, alpha can be calculated as the arcus tangent of the ratio of countercathete through encathete. In our triangle, the countercathete equals the cube's edge length, the encathete equals the face diagonal, or the cube's edge length multiplied by the square root of 2. In addition to this angle, we also need the ratio between the radii of the small and the large sphere, r2 divided by r1. For calculating this ratio, let's have a look at the distance from the sphere's center to a vertex of the cube. This distance equals half of the s, or half of the cube's edge length multiplied by the square root of 3. At the same time, it also equals the sum of the radii from the larger and the smaller sphere plus the distance from the smaller sphere's center to the cube's vertex d2. This equation will help us calculate the ratio between R1 and R2, but we still have to do several substitutions. The s can be replaced by R1 multiplied by the square root of 3. R1 can be replaced by half of the cube's edge lengths, and D2 can be replaced by R2 multiplied by the square root of 3. With these substitutions, we can solve our equation for R2. Finally, since we need the ratio of R2 divided by R1, we divide this equation by R1 or by 0.5a and end up with our factor. With this information finally obtained, we can set up our inner loop. For each large sphere from a previous loop, we define 8 smaller spheres scaled by the ratio just defined. These spheres are first located in an equatorial position, touching the large sphere, and then rotated around the z-axis by either minus or plus alpha. Finally, they are rotated around the y-axis for obtaining their final positions. After this inner loop is finished, the outer loop redefines the smaller spheres as the new larger spheres, and the inner loop starts for all new positions again. After this rather detailed discussion, I will only shortly touch my other examples. As always, you can take a look at respective scripts in my GitHub account. This example here has 4 spheres within a sphere as its basic motif. I have repeated this motif on 6 different levels and cut the whole structure open. I also tried other ways of revealing the arrangement, but sectioning worked best. I only want to show you one further example. The basic motif for this fractal is shown here. With each level, it is scaled by 1/3, and the elements from the previous level are surrounded by 20 of the smaller elements. After 4 levels, as shown here, there are already 8,000 small elements hardly recognizable as separate entities. This is all for today. I hope you enjoyed it. Next time, I will be talking about how to build up planar structures. This was one of the most difficult tasks I was confronted with in Porphyry, and the solutions I came up with are not perfect. Nevertheless, I will show them to you. Maybe you can come up with something better.